Okay, it is time for the new topic of today. All semester long, we haven't talked about exponential functions. So finally, after today, you will feel comfortable with differentiation and integration of exponential functions. We're going to stay primarily focused on e to the x. So we'll work through some examples together and then give you guys a chance to try some for yourself. So this will be part 1 of 2. In part 1, I would like to stay focused on derivatives. By today, we know that if we know a derivative rule, we can then write the corresponding integration rule, but I'll save that for the next video. So let's begin with the most basic derivative involving e to the x. So the derivative of e to the x is actually just e to the x. And this would be a fun exercise to try on your own sometime, just to consider graphically what this means. But because it's very frequent to see the exponent on e being something other than x, I'd like to try writing the rule one other way. So another way to write this rule would be to state that the derivative of e to any power can be expressed as e to whatever that power was, multiplied by the derivative of that power. So I'm just using a little block or a box to hold the place of whatever the exponent is, and then stuff prime right here to say that's the derivative of the power. So although the first form is more what you'd see in a textbook, the bottom form may be of value as we work through some derivative examples together today. So let's go ahead and dive in. I've got just a couple examples to try out, and then I think you'll feel prepared to do some on your own. This first example asks us to differentiate e to the x squared multiplied by sine of x. So in case I haven't made this point clear, we do still have all the derivative rules from the past on the table. So when we hear e to the x squared times sine of x, hopefully we begin thinking almost right away about a product rule. So this is the product of one function being e to the x squared and the other function being sine of x. So to differentiate, let's walk through this one using the power rule. Our power rule, again as just a little reminder, says that if we have f, g, quantity prime, that's the same as f, g prime, added with g times f prime. And you may know it in a slightly different order, so whatever way you've been using all semester, just keep using that and you'll be good to go. But I'm going to go ahead and work it out in this order. So to differentiate this given problem, I'm going to begin with y prime equals. So I'm going to keep the first function the same. So I'm going to carry over that e to the x squared. Then I need to multiply that by the derivative of our second function. Well, we know quite well that the derivative of sine is cosine. So that takes care of the first times the derivative of the second. Next, we'll add on the second, which is sine of x, multiplied by the derivative of the first. So here's the first time today when we get to use this new knowledge of differentiation with e to a power. So we need to differentiate e to the x squared. And so far we understand that the derivative of e is itself, so I'm going to copy down e to the x squared. But then I need to multiply it by the derivative of the power. In this particular case, the derivative of the power, which is the derivative of x squared, would be 2x. So that's probably the hardest part of this first example, just getting used to the fact that the derivative of e to a power is itself, meaning the same exact thing, times the derivative of that power. Let me just go back briefly to the derivative rules page here. When we differentiate e to the x, we got just simply e to the x, and the reason for that was because if we were to show timesing by the power, the derivative of the power of x would just be 1. So we don't typically show multiplication by 1, but technically you could think of it in that way. So let's just make sure we're okay with this first example. Applying the product rule, quick summary, we took the first function, which was e to the x squared. We multiplied it by the derivative of the second function. The derivative of sine was cosine. So there's our f and our g prime. Then to that we added function g left alone. And then we multiplied by the derivative of f, and that's the part that today required our new knowledge of the derivative of e raised to a power. So hopefully that feels good. Again, pause at any time to discuss a little bit, but if I think back to e to the stuff, right? The stuff in this example was x squared, and then stuff prime was the derivative of x squared, which was 2x. So that would be it for this one. So we can leave our final answer. I'll just go ahead and bubble it off so we know we're good. I'm not going to bother showing more simplifying. This should be enough for today just to differentiate. All right, let's try a couple more. They can't all be quite this way. So the next example I have actually looks strikingly similar to the first one. You'll notice that what I did in the second example is I just put everything up as the exponent on e. So in this first example, we had a product between e and a trig function. In the second example, we have e raised to the product of x squared and sine of x. So the technique for differentiation here will be a little bit different. This would actually be, in the big picture, a chain rule problem because we've got e to a power. So let's begin with what we know. So far our understanding is that the derivative of e is itself. So for starters, I'm just going to copy down the exact problem we began with, which was e to the power of x squared times sine of x. Now what we need to do is multiply by the derivative of that power. So if you think back to the way I wrote the definition earlier, which was that the derivative of e to the power of stuff is e to the power of stuff times stuff prime. So far we're just showing the first part, right? We've written down e to that exact same power. Now let's go ahead and dive into the derivative of the power. How do we differentiate x squared times sine of x? Well, that's actually going to take a power rule, right? So we've got a little first function and a little second function. So we're going to jot down the first function. There's the first function. We need to multiply that first function by the derivative of the second function. And the derivative of sine we know is negative cosine. Having some trouble with my dots versus negative, sorry. So x squared times negative cosine of x. Then to that we need to add on sine, and we need to multiply sine by the derivative of the first function. The derivative of x squared will be 2x. So let me just make sure those pieces of the product rule look okay to you guys. So we did the first, then we did the derivative of the second, and we added to that the second multiplied by the derivative of the first. So that would be it. Again, if you choose to simplify a little further, I'll leave that up to you. But focusing on the actual derivative rules, we have now differentiated the given function. So a little different approach between the first two examples. In the first one, the big picture was a product rule. In this last example, the big picture was the chain rule, and the product rule was included within that chain rule. All right, I can tell you're all having so much fun, so for that reason I'm going to do at least 2 more examples, just so we all have a great time. Here's another good example. This one should look similar to things you've seen from the past. You guys are very comfortable with radicals. A good first step from calculus, of course, would be to rewrite radicals with rational exponents. So since we've just got a square root in this problem, I'm going to rewrite that square root as a power of 1/2. And so hopefully we view this problem, big picture, as another chain rule. So we've got a quantity being raised to a power. So what's the chain rule going to say about that? Well, we've got to take the derivative of the outer function, which in this case is really the square root. So we're going to start by bringing down the power. we're going to keep that inside function the same. Let's see if I can bring in another color here. So how about we keep the inside the same? What else needs to happen? We should be reducing the power on the parentheses by 1. So a half minus 1 is a negative half. So far we've taken the derivative of the outer function and evaluated at the inner. What's still left then is we need to show multiplying by the derivative of the inner function. So the derivative of 5x squared plus e to the x cubed would be 10x as the derivative of 5x squared. And how about the derivative of e to the x cubed? That should be itself. So e to the x cubed multiplied by the derivative of the power. The derivative of the power is the derivative of x cubed, and that's 3x squared. All right, so in terms of big picture being chain rule, looks like we've tackled this one just fine. To run through those steps again, when we have a quantity raised to a power, the power comes down, the inside stays the same, we reduce the power by 1, and then we multiply by the derivative of the inside. So hopefully that felt pretty comfortable for us to look at the derivative of e to the x cubed. The derivative of e to the x cubed was itself, e to the x cubed, multiplied by the derivative of the power, and that's where we got that 3x squared from. So final answers here. Not going to bother in this video with any simplifying steps, just leave it at the place where calculus has been completed. All right, one more you say. Perfect. I think I got one more and then I'll ask you guys to try a little practice, so bear with me for one more example. This one says to differentiate sine of a quantity. And that quantity is more complicated than just x. So right off the bat, in terms of big picture, what do you all see this as? Is this a chain rule, a product rule, a quotient rule? I think I heard chain, right? So it should be a chain rule. And actually it seems like it's going to be chain rule within chain rule. So we'll talk about that as we go through it. So let's go ahead and start by saying the derivative is y prime. And the outer function, if you like to think about it in that terminology, would be the sine function. So the derivative of sine is cosine. And we need to start by evaluating cosine at the original inner function, which was e to the 2x plus e to the negative 2x. So far we've taken the derivative of the outer, evaluated at the inner. Now we just need to show multiplying by the derivative of the inner. And this is where I feel like it's really a chain within a chain, because the derivative of e to the 2x is itself times the derivative of the power. So that's really a chain rule step there. And similarly, the derivative of e to the negative 2x would be e to the negative 2x times the derivative of its power, which is negative 2. So a little different feel for each of these examples. This one again was another chain rule. So we began by deriving sine to get cosine. We evaluated cosine at the original inner function, and then we multiplied by the derivative of the inner function, which technically required 2 more small chain rules, if you like to think about it that way. So hopefully some of these examples make a bit of sense. Feel free to discuss any of the examples we've done so far as a class. But once you feel comfortable, I'd love to have you trying some practice. So here's the goal. Once I've gone through these steps, you can go ahead and pause the video. Don't pause it quite yet. But after I run through these steps, you can pause it and then grab markers and try homework 3B, problems 1 through 7 on the whiteboards. You can work them in small groups like we typically do. And then take a little bit of time to critique each other's work. Make sure you agree upon those answers. Once you feel pretty good about them, if somebody could please take some photos. I think we nominated Jackie to take some photos, or whoever is willing, just so I can see what you all did do as a class. And then once you've done that, feel free to hit play on the video, and I'll just go through the solutions for those 7, and hopefully our work, or my work here, matches the work you guys have on the boards. So go ahead and pause this video and give those a shot. Give yourselves about 20 minutes to try those, and then hit play. Have fun. Did you really hit pause, or are you just watching the answers? You tried them out? Okay, here we go. So compare real quick against your work on the boards. I won't take too much time here. But homework 3B, problems 1 through 7, were all problems involving differentiation. Problem number 1, big picture, was a product rule. So we had the first function multiplied by the derivative of the second function. So first function times derivative of second plus second times derivative of first. Hopefully that looks real good. If you took it further in terms of simplifying on the board, no problem. As long as our first calculus step matches, we should be good. All right. The second one really was a chain rule. So the derivative of e to a power is e to that same power times the derivative of the power. So hopefully you all got e to the x cubed times 3x squared for problem number 2. If we're still good, problem number 3. Big picture was a product rule. Within the product rule, we could say there was a little chain rule action. So we had the derivative of the first, we had the first times the derivative of the second, which is arguably where a chain rule happens, because the derivative of e to the negative x is itself times the derivative of the power. And then we added to that the original second function times the derivative of the first. All right, looks pretty good, hopefully. 4, if you were to describe the steps required, it is a chain rule with a product rule inside of that chain rule, and then technically within that product rule, there's a chain rule. That sounds hopefully more confusing than it actually was. So the derivative of e to a power is itself, that's this first piece here, multiplied by the derivative of that power. So you can see to multiply by the derivative of t sine of 2t, that's technically a product. So we show the first times the derivative of the second, which is a little chain rule, plus the second times the derivative of the first. So in terms of a first calculus step, hopefully we had that. If you all chose to simplify further, that's wonderful. 5, we saw an example kind of like this one. Looks like a big chain rule because we've got a radical with stuff underneath it. Hopefully you started by rewriting that radical with a 1/2 power so that we could see the power comes down. The inside stays the same. We reduce the power. Oops, now I'm reducing the power by 1 to get a negative 1/2. And then we're timesing by the derivative of the power. The derivative of 1, we're timesing by the derivative of the inside. And the derivative of 1 was just 0. The derivative of 2e to the 3x is itself multiplied by the derivative of the power. All right, number 6, this one just looks kind of weird, but we're differentiating e to the x. Well, the derivative of e to a power is itself, and then we just had to times by the derivative of the power. Well, the derivative of e to the x is just e to the x. So that one probably looked worse than it was. Final answer there, e to the x times e to the x. All right, last but not least, 7. May have been a little messy since at least the way I worked it here was through quotient. First of all, big picture though is a chain because we've got cosine of a fairly complicated quantity. So we take the derivative of cosine, which is negative sine. We evaluate it at the original insides, and then we multiply by the derivative of the inside. So I chose to use quotient, so I should have the lower function times the derivative of the upper function, which required a little chain rule, minus the upper function times the derivative of the lower function, which required a little chain rule, all divided by the lower function squared. So I hope that went really well for all you guys. Give me some feedback, but we'll go ahead and move into the integration side of exponential functions.